Okay. Hello. Today what we will look at is finding the maximum or minimum of a graph without actually sketching it. So let's say you're given the graph y is equal to e to the power of x over x. Now to find the minimum, you obviously need to work out your critical points. You get the critical points and then you test them using the second derivative test. If when you substitute your critical point into the second derivative, your answer is positive, that means you have a minimum. If it's negative, that means you have a maximum. So to find our critical points, you take the first derivative. Here we have to use the quotient rule. So it is the denominator as it is, the derivative of the numerator, which is just e to the power of x, and then minus the derivative of the numerator of the denominator, which is 1, and then multiply this by the numerator as it is, then your denominator is squared. Now the critical points, so at the critical point we have y prime is equal to 0, so we can equate this. We have x e to the power of x minus e to the power of x over x squared. This is equal to 0. This means that x e to the power of x minus e to the power of x is equal to 0. You can factor out e to the power of x. This means x minus 1 is equal to 0. Now we know e to the power of x is not equal to 0. There is no exponent that you can substitute for x to make e to the power of x 0. So that leaves us with x minus 1 is equal to 0. So we say that since e to the power of x is not equal to 0, for any x that you substitute in there, you will never get e to the power of x equal to 0. So if x minus 1 is equal to 0, this means that x is equal to 1. Now I will need to test this critical value and see whether it is a maximum or a minimum. To test it, I'll use the second derivative. So my second derivative is just the derivative of the first derivative, which is this one over here. And again, I will use the quotient rule. So it is the denominator as it is, and then the derivative of the numerator, which is x e to the power of x plus e to the power of x, then minus e to the power of x, and then the derivative of the denominator, which is 2x, and then the numerator as it is. Then my denominator has to be squared, x squared squared. This is just x to the power of 4. Then if you simplify, what can be simplified? You'll notice that these two will cancel each other out. Then what I will be left with is x to the power of 3 e to the power of x minus 2 x squared e to the power of x plus 2x e to the power of x over x to the power of 4. Now when I look at all my terms, they all have x in them, so x can cancel. And then what I have is this, or I can factor out x e to the power of x out. So I have x e to the power of x. I am left with x squared and minus 2x, and then plus 2. This is x to the power of 4. Okay, then the x and the x to the power 4 can cancel. So what I have left is e to the power of x. Then I have x squared minus 2x plus 2 over x to the power of 3. So that is it in its simplest form. Now what I do is I will use the second derivative test. That means I will substitute x is equal to 1 into the second derivative. So I'm looking at y double prime of 1. This is equal to e to the power of 1 squared minus 2 times 1 plus 2. This is divided by 1 to the power of 3. Okay, this is just equal to e, and we know that e is greater than 0. So when our second derivative gives us a value that is greater than 0, we know that we have a minimum at x is equal to 1. And then we can work out the y coordinate. So y is equal to e to the power of 1 over 1. This is just e. So the minimum point is 1, comma e. And that's how we would do that one. Now there are some other applications of differentiation. So curve sketching is one of them. Another is maximization and minimization. So we want to maximize and to minimize. Okay, so that is one of the applications. If we want to find out what is the maximum of something, what is the minimum of something, we can also use derivatives to do that. Now, one such question is if you are told that you want to make a can. The can has a fixed volume, and you want to minimize your material that you use in making the can. Because if you use a lot of material, you're going to spend a lot to pay for that material. Now the volume is fixed, so this has a volume is constant. So that means beforehand you have already decided what your volume will be. And what we want to find out is what is the radius that we should have here so that our area is minimized. Okay, because if we use minimum area, we're using minimum materials. Now we know that our area is given by this formula. So our area, this is equal to 2 pi r squared. This is the area of the circles on top as well as the circle at the bottom. And then 2 pi r times h. Okay, so that is the total area of the can. Now this h over here, that is the height. That is the height of the can. Okay, and we know that if we take a cylinder and we cut it open, what we end up with is a rectangle. So to get the area, we say this part over here, which is the circumference, is going to be my length, and then the height of the can is the breadth of the rectangle, so I just multiply them. Now here I do not want to use h because that will be another variable, so what I will do is rewrite h in terms of the volume. So I'm going to show that this area here, the area of the rectangle, this is equal to 2 pi rh. So we've already said that if you take your can and you open it up, you will get a rectangle like that. So this part over here is 2 pi r, and this is h. Then you multiply them, that's where that formula comes from. Now, we know that the volume of the can, it's a cylinder, is given by this pi r squared times the height. That is the volume of the cylinder. Now what I will do is I will make h the subject of the formula here, and then substitute it into this equation there, because the volume is constant. It's a fixed value. Here we're not told what the volume is actually, but it is fixed, so you can take it as a number, unlike h over here, which you may look at it as a variable. So what I do is, if I have my volume over here, I can multiply both sides by 2. So I have 2 times the volume. This is equal to 2 pi r squared times h. And then if I divide by r on both sides, divide by r, you'll see that I have 2v over r. This is equal to 2 pi r h. Now this 2 pi r h, this is the area that we said we have over here. So I'm going to replace this with what I have worked out over there. So my area of the cylinder becomes 2 pi r squared. That is the 2 circles, the one on top and the one at the bottom. And then I add 2v over r. Now my equation is only in terms of r. Now I say that again because v here is a constant. It is a specific number. So you've already decided I want to make my can 500 millimeters if you want to, or whatever. So that is a fixed volume. It is not a variable. Then what you do, because we want to minimize, we always have to work out our critical points and then use the second derivative to test them. So I find dA dr, and this is equal to 4 pi times r. And then over here, this r, this is the same as r to the power of -1. So the -1 will come down. So I have minus 2v, and then the -1 will decrease by 1 to become r to the power of -2, which is just r squared, like that. So that is the first derivative. Okay, so again, remember that v is a constant, so I do not multiply by dv dr because v is fixed. Then for the critical points, dA dr is equal to 0, so we have 4 pi r minus 2v over r squared. This is equal to 0. Then to solve this, want to work out the value of r, what we do is we have 2v over r squared, and this is equal to 4 pi times r. Okay, we can multiply by r on both sides, so r squared rather. This is 4 pi r cubed, and then divide by 4 pi on both sides. Divide by 4 pi, divide by 4 pi. Then I have r cubed. This is equal to v over 2 pi. Now I'm interested in r, so I take the cube root on both sides. So r is equal to the cube root of v over 2 pi. Then I have to use my second derivative to test whether this is indeed a minimum or not, because remember I want the radius that will give me the minimum area Okay, so D2A, dr2. Here I'm going to differentiate my first derivative. The first derivative is this one over here. So I'm going to differentiate that. When I differentiate 4 pi r, I will get 4 pi because r power 1 will come down. And then when I differentiate this one, this r to the power of 2, that's the same as r to the power of minus 2, sorry, when it goes to the numerator. Then when I bring that down, this will become positive. So let me write that down. Okay, let me first rewrite the first derivative. So dA dr, we said this is equal to 4 pi r minus 2v, and since it's over r squared, I can write this as r to the power of minus 2. Then when I get the second derivative, this is 4 pi, and then for this one the minus 2 will come down, multiply that one, I get positive 4v r to the power of minus 3. This is just 4 pi plus 4v over r to the power of 3. Now this is already positive. I don't even need to substitute my r inside, because I can see that this is a positive number. 4 times pi is positive. 4 times v is positive because your volume must always be positive. R cubed is also positive because your radius is positive. So this is greater than 0. So whatever critical value I substitute in there, I will get a positive value. So for any critical value, it is a minimum. Okay, so what this means is if I want to get a minimum area, so I do not want to use a lot of material, and I'm interested in finding out the radius that I should use to make this can, the radius should be equal to the cube root of my volume, and then I divide this by 2 pi. Now the question continues, or in the exercise it says if the volume of the can is 340 millimeters, remember 340 millimeters is 340 centimeters cubed, what should the radius be? Here we just substitute, and then we have 340 centimeters cubed divided by 2 pi. This will give us approximately 3.27 centimeters. And in the textbook, you're asked what is the actual value. The actual value is pretty close to that, but it's not exact. And then the reason is, why is that? Why is it not exact? One of the reasons might be the measuring equipment that you use. It's not exact. Another thing is you can think of the manufacturing processes, the human errors that can happen. So it is that this one here, this is the ideal, that then you would have the absolute minimum area. But in real life, it is very, very difficult to get the ideal. So you'll notice that what you have is close to the ideal, but it will very rarely be exactly that. So let's look at some more questions. These are questions in exercise 12.12.3. This is number 2. Now with this question, you are told that a farmer wants to fence off some land. So he has 100 meters of fencing and he wants to create a rectangular sheep pen with one boundary along a stream. So what you have is this So you have a stream over here, it's a stream of water, and then he has a fence which is 100 meters long, and he wants to create a rectangular pen. So he wants to create something like this. So the sheep are kept in there. They will not go into the water, I assume, so they are safe. And we want to find out what the maximum area of the pen can be. Right, so we know that this pen over here is the material that is used to make it should be 100 meters because that's what he has. So when you make a rectangular pen, this side, if you call it X, this side will also be X, and then this one over here will be Y. Now we know that X plus Y plus X, so the length there, X, length X there, this is equal to 100 because that is all the material that he has. Now if we simplify this, we have 2x plus y is equal to 100. Now we're trying to minimize the area, so we say our area, this is a rectangle, the area of a rectangle is just x times y. Now this equation here is in terms of x and y, and we want to change one of the variables and rewrite it in terms of the other one. So what we can do with this equation over here is rewrite it where y is the subject of the formula. So from star, I will get y is equal to 100 minus 2x. Then I will substitute the y over there and have a single equation in terms of x. I'll find the critical points, test them, and see if it gives me a maximum area or not. So the area, this is equal to x times y, which is 100 minus 2x. So when you multiply this out, this is 100x minus 2x squared. All right, so just by looking at this, what you have over here is a parabola. It has a parabola that opens downwards, so already you should know that this will give me a maximum value. So parabola that opens downwards has a maximum value somewhere there. Okay, so we find the first derivative, we find dA dx. So dA dx, this is equal to 100 minus 4x. Okay, then the critical point happen where the first derivative is equal to 0. So the critical point, we say 100 minus 4x, this is equal to 0. This means that 4x is equal to 100, and therefore x is equal to 25. So now that x is equal to 25, I need to use the second derivative to test if indeed this is a maximum point. So I need to work out the second derivative. So this is d2a dx2. This is equal to, I look at my first derivative, there it is. When I differentiate this, I will get 0, which is the derivative of 100, and then the derivative of minus 4x is just minus 4. And this is less than 0, that means I will have a maximum. So the second derivative gives me negative 4, doesn't matter what the critical point. So for any critical point, it is a maximum. Okay, so any critical point we work out will be a maximum critical point because the second derivative gives us a negative. Okay, so now that I know it is indeed a maximum, I can go back to my drawing. So we said we have the river over there and then the enclosure. We said we have x over here, so this x, and this is equal to 25. This side will also be equal to 25. So this side over there and that one, when I add them together, it gives me 50, and that means that this side y is equal to 50 because the entire length must be equal to 100. Okay, so we can also calculate what the maximum area will be. So our maximum area, this will be 25 times 50. And this is equal to 1,250 meters squared. Okay, so that is the maximum area. And you can try it with other values. Let's say, for example, you want to make this 10, 20, and you make this 80. So if you make this 10 and you make this one 80, so that's obviously 10. The entire length is equal to 100. The area over here is 800, which is less than what we got over there. Then you can see, okay, what if I try and make the two sides closer in length? Let's say you use 30 and then 40. So this side is 30. This side will also be 30, so that's 60. You're left with 40 over here. If you work this out, you get 1,200. Okay, which again is less than that. So you will not get an area that is bigger than that one, no matter how hard you try. So that is why that is the maximum area. And number 3. With this one, you are told that a rectangle has a perimeter of 50 meters. We have to find the length and the breadth, which gives the maximum area. So you have a rectangle. This is your rectangle. And we are told that its perimeter is equal to 50. So perimeter is equal to 50. And what we want to do is work out the maximum area. So this is similar to the one with the farmer, except in this case you are making the whole pen out of the fencing. You're not using a river or wall or a boundary on the other side. So we know that our perimeter P, this is equal to 2x plus 2y. So we get the perimeter by saying x plus y plus x plus y. That is the perimeter. And this is equal to 50. So when we simplify this, this just means x plus y is equal to 25. Now the area, this is what we want to maximize, is given by a is equal to x times y. And then what you do here is you will substitute x or y, one of them. You make them the subject of the formula in this equation star, and then you will substitute them into the equation of a, and then find the critical points. So doing that on star, I get x is equal to 25 minus y. Then I will substitute that over there. So I have a is equal to 25 minus y times y. Then we'll multiply that. So this gives me 25y minus y squared. So again, here from drawing our conic sections, remember that this is a parabola that opens downwards, so it has a maximum point. So even before I test it, I already know I'm on the right track because I'm going to get a maximum point. So now that I have that, what I do is I find the first derivative. So this is a prime. This is 25 minus 2y. Then the critical point, I set a prime equal to 0. So I have 25 minus 2y. This is equal to 0. This means that 2y is equal to 25. And that means that y is equal to 25. over 2. Okay, now if y is equal to 25 over 2, I need to test it to make sure that it is a maximum. So my second derivative, which is a double prime, this is the derivative of the first derivative. So the derivative of 25 is 0, the derivative of minus 2y is just negative 2. So this is negative 2, which is less than 0, and therefore I have a maximum. Okay, so when I substitute that a double prime of 25 over 2, this is equal to minus 2, because your a double prime is a constant function. Whatever you put into the function, you get minus 2 out. So it is indeed a maximum. So now that I know the value of y, I can work out the value of x. So we say that x is equal to 25 minus y, which is 25 over 2, and this gives me 25 over 2. So my rectangle turns out to be a square, where one side is 25 over 2 and the other side is also 25 over 2. Then you can work out the maximum area. The maximum area, this will be 625 over 4, and this is in meters, so we have meters squared. But we're not asked to work that out, to just say find the length and the breadth. So you can also write a statement: length is equal to 25 over 2 meters, and the breadth is equal to 25 over 2 meters. So if you have fencing wire and you want to use that wire to make the maximum area will always be a square. Then look at the next one. In this one, we are told that the difference between two numbers is 20. We have to find the smallest product. So your two numbers, you can call them x and y. So you have your number 1, this is x, and then number 2, this is y. Now we are told that the difference between them, that means x minus y, and this is equal to 20. And the product of the two numbers is just x, y. So we want to find the smallest product. So smallest product means minimum value. So as usual, from this equation over here, we will make x or y the subject of the formula and then substitute it into the other equation. So doing that, I have y is equal to x minus 20. And this x minus 20 is what I will substitute over there. So I will have the product is equal to x, and then y is x minus 20. And we multiply. This is equal to x squared minus 20x. And then I will do the usual thing. I'll differentiate, work out my critical points, then substitute them into the second derivative to see if I will get a minimum. Now just by looking at this is the equation of a parabola that opens upwards. So this is what it looks like, and such a parabola will have a minimum point. So we find dp dx. This is equal to 2x minus 20. Then the critical point, this means 2x minus 20 is equal to 0. This means that 2x is equal to 20, and therefore x is equal to 10. So my critical point occurs when x is equal to 10. And what I do is I use the second derivative to test and prove that this is indeed the minimum value. So I find the second derivative. So this is 2p dx2. So my first derivative was 2x minus 20. When I differentiate 2x minus 20, I will get 2 minus 0. So this is just equal to 2. And we know that 2 is greater than 0, which means I will have a minimum. So when I substitute my critical value, x is equal to 10, the answer will be equal to 2 because the second derivative is a constant function. Whatever you substitute in, your answer will always be equal to 2, and that tells me that I have a minimum value. Okay, so now that I've shown what the x value is, that will give me a minimum product. All I need is the y value. So remember, I said y is equal to, where is the equation? Here, y is equal to x minus 20. So x is 10 and then minus 20, and this is equal to minus 10. So the two numbers are 10 and minus 10. So you can work out the product. This is equal to minus 100, and you can try it with any two other numbers whose difference is 20. You will see that the product is bigger than minus 100. So minus 100 is the smallest product you can get from numbers whose difference is 20. And then the last one, number 5. With number 5, we are told that you have to make a rectangular box that is open at the top from a metal sheet. So you have a metal sheet like this. This metal sheet is 10 centimeters by 16 centimeters. Now what you will have to do in order to make this rectangular box is you need to cut out squares at the corners like that. So you need to cut out squares like that. And then when you end up with something like this, what you will do is you will fold the corners up, and then you end up with a box that is open at the top, which is what you want. Now the question is, what size squares should we cut out over here so that we have the maximum volume? Okay, so we have a sketch. With these questions, it's always good to draw a sketch and then you visualize what it is you need to do. Now, the squares that we are going to cut out will all be the same size. So I'm not going to cut out 4 different squares. It is the same kind of square from all the corners. Now, this square will have dimensions x by x. So this is x, that is x, 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 and x over there. Now this part over here that is left is 10 minus 2x. So you've cut out x there, and you've also cut out x over there. So what is left is 10 minus x. So let me write it over here. Okay, so you will have here, you'll have 10 minus 2x over there. And then in the same way, this side you will have 16 minus 2x. And then the bottom of your box over there, this side will be 16 minus 2x, this side is 10 minus 2x, and then the height of the box will be x, because that's the part you cut up. So this side is going to come up and be the walls of your box. So try and visualize that one. Then our formula for the volume is going to be the base area multiplied by the height. So this is 10 minus 2x multiplied by 16 minus 2x, and then the height, which is equal to x. So this is what we want to maximize. So first we should multiply out the brackets. We multiply out the brackets. We have 160x minus 20x squared minus 32x squared plus 4x cubed. So 10 times 16 times x, that's where I got that one. 10 times negative 2 times x is negative 20. Negative 2x times 16 is 32 times x is 32x squared. Negative 2x times negative 2x is positive 4x squared times x is 4x cubed. Then when you simplify this, this is just equal to 160x minus 52x squared plus 4x cubed. So we have that one there. Then we have to find the first derivative. So dv dx, and this is equal to 160 minus 104x. So the 2 over there comes down and multiplies with the 52. That's why I get the 104. And then plus 12x squared. Okay, and to find the critical points, we set this equal to 0. So the critical point, dv dx, this is equal to 0. Then what we have is 160 minus 104x plus 12x squared. This is equal to 0. So I can divide by 2 throughout. First, let me rewrite this. This is just 12x squared minus 104x plus 160. This is equal to 0. Okay, or I could just divide by 4. See, that is also a common factor. So divide everything by 4. Okay, so what I get is 3x squared minus 26x plus 40. This is equal to 0. So what I do now is I can solve this using completing the square, factorizing, or the formula. So when you factorize this, you end up with 3x minus 20. Then I have x minus 2, and this is equal to 0. So it's factorized. Then what I do is I solve each of them. And 3x minus t is equal to 0. This means that x is equal to 20 over 3. Then the second one, x minus 2 is equal to 0. This means that x is equal to 2. So I have my 2 points over here. One of them should give me a minimum. So remember when we drew the cubic functions, it had a maximum and a minimum. We had to distinguish them using the second derivative test. So now the second derivative test. we have to work out the second derivative. So to get that, I differentiate the first derivative. The first derivative is this one over here, not the one where you divided by 0. It is the original one you started with. So this is minus 104 plus 24x. Now notice this is not a constant function, so it depends on what your x is. But you know the test, if your second derivative gives you a positive, then you have a minimum. If it gives you a negative, then you have a maximum. So you substitute both the critical points into function. So here we have x is equal to 20 over 3. When I substitute that, what I get is negative 104 plus 24 times 20 over 3, and this is actually equal to 56. Now 56 is positive, so this will give me the minimum volume, but that's not what I'm looking for. I'm interested in working out the maximum volume. So the other one should give me the maximum volume. So I substitute x is equal to 2, and I have negative 104 plus 24 times 2, and this gives me negative 56. Negative 56 is obviously less than 0, so this gives me my maximum volume, which is what I'm looking for. So here we can just note we will get a maximum volume when x is equal to 2. Okay, so in the text it says describe how the box must be made. So you can just describe it. We will get a maximum volume by cutting squares of length 2 centimeters from the corners. Okay, and then you can work out the maximum volume just for interest sake, or in another question where it is asked. We know that the formula for the volume is 160 times x, which is 2, minus 52 times 2 squared, plus 4 times 2 cubed. So this one you do on your calculator. Okay, and then you would get 144 centimeters cubed. And then for interest sake, you can also work out what the area would be if you cut out squares with lengths 20 over 3. So this is just for interest sake. So if x is equal to 20 over 3, you would get volume, which is equal to 160 times 20 over 3 minus 52 times 20 over 3 squared plus 4 times 20 over 3 cubed. So again, this you do on your calculator. Okay, and we get a negative value. So I'm getting minus 59.259. This is centimeters cubed. And this is not even possible, okay, because you cannot have a volume that is negative. But if you were to sketch this graph, you will see that this is the minimum y value, like that. Okay, so those are all the questions that are given in your notes. There are lots more on the internet that you can work out, maximizing or minimizing. The procedure is always basically the same. What you do is you must, if you have more than one variable, like we did with the x and y, the rectangles or the numbers, you must make one of them the subject of the formula and then substitute it into the other equation, differentiate, equate your first derivative to 0, then you test your critical point if it is a maximum or not. So even if you can tell, like we were able to with the parabolas, with the parabolas like this one, I can see from the equation that this is definitely a minimum, but I still have to do the second derivative test. Okay, so go and try some more and then we'll talk in the next class. If you have questions, just email me, call me on Teams or on e-learning, and I'll get back to you.